So this is the first problem solving session. Nobody has come in and I didn't get any requests in the forum. So in the future, if this happens, there just won't be a recording. But there was some material that I wanted to kind of touch base on. I had picked some problems to go over and I was going to incorporate anything that people asked about. So I'll just go ahead with what I had wanted to cover. Right now I'm showing you the Blackboard for our course. I just kind of wanted to make sure that everyone saw in a recording in case they didn't quite catch it during lecture on Thursday. This is where you'll get all the material you need. Right now I'm at the course basics tab where there's the syllabus, link to your web work, information about office hours, including this session, and then the way to contact me, because if you contact me via email, there's a good chance your message will get lost in my inbox. And then right now is the virtual problem solving session. So if you ever wanted to contribute to that, you just navigate to that tab. Sorry, all these pop-ups. And then there's always going to be a forum that opens up for the current week. And then if you go there, you could create a request. Right now I see that there are no items because nobody made any requests. And then the Zoom link if you want to join live. Otherwise, I'm going to post them in this playlist right here. And then just from the first day of class, there was this worksheet that I handed out, a copy for each group, but then there's also the digital copy. In case you missed it, it's under the class materials tab. And if you just click that, you'll see the exact same PDF that I handed you in person. That kind of talks through how to do the first web work assignment. And so this recording right now is going to be about that web work assignment. So bear with me as I try to get the technology working exactly the way I'd like. A lot of what I say is going to be briefly recapping what's in this PDF. And then I'm also going to go ahead and navigate through the web work so you can kind of see everything at the same time. So this review was designed so that you could kind of read a bunch of definitions really quickly and then apply things that are really intuitive to you or things that you already know, and then only have to listen to me talk about the things that are newer to you. So go ahead and skip to the thing that you need if you're watching this video. The first several problems, I'd say WebWorks 1 through 5, I've really not gotten questions about. So those are just sort of the definition of a vector and then how we do vector addition, how we find the distance between 2 points as a vector, how we find the length of a vector. And so if you just go down the line of the worksheet, after you read the first paragraph, you're going to learn how to write a vector from a given point, and then your first web work is to find a point and then write the corresponding vector. No, I needed to move forward here. Second one corresponds to this second block, which is if you want to write a vector that goes between 2 points, you just follow this formula. The main problem I'm seeing with people here is that if you have like something minus a negative, that does become addition. So just be careful with the arithmetic here. And same as we move on to problem 3, there's just a brief description of how we add and subtract vectors component-wise. And really the only issue I'm seeing here is that sometimes subtracting and adding aren't going quite right. The other thing that I'm seeing here sometimes is, for example, this A equal to J hat plus 4K hat. Oops, I think it was J hat. Just so you know, that's actually 0 I hat plus like 1 J hat plus 4 K hat. So sometimes people are wondering, how do I add with something that has an I hat and something that doesn't have an I hat? Anytime you don't see that I hat, it's because it's a 0 and it's just kind of hidden. Otherwise, I don't think anything really fancy is happening in those problems. Problem 4 is kind of more of the same, just now it becomes an algebra problem, taking it one step further. And then problem 5 is applying that length formula that people seem pretty happy with in class. So I'm not going to belabor that point. Problem 6 about unit vectors, I'm actually going to go into in more detail in a little bit, so we'll skip that for now. Same with problem 7, where just completing the square is kind of a challenge for people. But then problems 8 through 13 are pretty much applying formulas again. So 8 takes you to definition of a dot product. If you just apply that formula, you'll be able to solve all these. And then 9 uses this, that's the doc version of it. 9 uses this angle property that's given in a formula here, so you just need to apply the formula to solve for that dot product. 10 is just using that exact same formula, but now making it into like an algebra question. So we combine the two definitions, and then for unknown theta, we're going to go ahead and solve this equation. So you'll just take the v and u you're given, and you'll plug everything in that you can. Remember that to get these lengths, you do have to go back to this formula up above. But then you'll have a bunch of numbers on both sides and unknown cosine theta, and just, do algebra and trig to get that angle that you plug in. Make sure you do it in radians. If you do it in degrees, WebWork will count it as wrong. So you might need to change your calculator settings to get that. Problem 11 is more of the same. So you've got your two vectors, and you can do the exact same process to find the angle between them as you had here. But now you're just going to ask yourself, once you know that angle, does that mean that they're orthogonal or perpendicular? That means the angle between them is 90 degrees. They're parallel. That means that the angle between them is like 0 or 180. Or neither. The angle between them is something else. Also, you can tell that two vectors are parallel if they're scalar multiples of each other. If you want to check that way instead, that's fine. 12 and 13 are still applying formulas, but it just moves on to the kind of like an application first of the dot product to make projections and complements. So you just use this definition for the projection, and then this definition for the complement. It's a bit of arithmetic to get your answers here. And then 13 is finding the cross product. So there's a formula here for how to find the cross product. And then I'm also going to show you the like matrix looking approach in more detail in a little bit, because some people like that. That's how I'll usually do it. And then problem 14 is an application of the cross product. So right here on your worksheet, it tells you the magnitude of the cross product is the area of a parallelogram formed between two vectors. So here you're going to be given vertices, and your first challenge is going to be to make some vectors between those vertices. That's going to take you back to like problem 2, I think it was. Yep, problem 2, make some directed line segments between those vertices. And then once you do that, the triangle is just sort of like half of a parallelogram between, for example, if you choose to do PQ and then PR, the triangle is going to cut right through the middle of a parallelogram formed by those two. So all you're going to do is follow this formula for the cross product. Know that the magnitude is going to be the area, and then if you know the area for a parallelogram, half of it is going to be the area for the triangle, and then you don't have to do anything to this vector. It will be the same as is given just from the cross product. And I'll write that out because I know it was a lot of steps to talk about just there. Problem problems 15 through 18 get a little bit trickier. They just start to combine different ideas. So 15 is just going to combine like problems 1 and 2. First, you have to find the vectors to the points, and then you do some arithmetic on them. That fourth one uses the length formula from a different web work problem. Problem 16 is going to be kind of like problem 11, where you were solving for angles. So you're given two vectors and you want to find the angle between them. And then instead of saying what the angle actually is, you're just going to classify it as obtuse, right, or acute. Right is 90 degrees, obtuse is more than 90 degrees, and acute is less than 90 degrees. So this is just combining a little bit of trig with those dot product problems. Problem 17 is again going to use the dot product property about perpendicular or orthogonal vectors. In this case, it's asking you to find some information about the vector from A to B and the vector from A to P. So kind of your first go should be, okay, I'm going to find the vector between A, B, and the vector between A, P, using that same approach from problem 2 in this section. And then it's asking when those two things are perpendicular. So anytime you hear perpendicular, you should think dot product. So you're going to go ahead and take the dot product between the two things you found, and then ask yourself what value of dot product would mean that they're perpendicular. You know, you just go back to your worksheet. Orthogonal means 90-degree angle. Cosine 90 is what? And then once you do that, you're going to have an equation with an unknown k in it, and you just solve for the k that gets you the value of the dot product that you want. If I have time in this session, I'll go ahead and write out those steps as well. And then problem 18 is kind of more dots and cross products. The only part that I thought might be tricky here is that you do need to know that the coordinate vectors are like 1, 0, 0, 0, 1, 0, and 0, 0, 1. These are like unit vectors in the x, y, and z directions. And so you could go ahead and just manually solve all these things knowing that. You could also think through, based on what you know of the geometric or like trig properties of the angles you saw between vectors. If I, j, and k are all perpendicular to each other, what should you get from their cross products? So that's sort of a brief overview of how to do each problem, and then I wanted to go into a little bit more detail with everything, but to do that I need to stick to this screen and stop showing you the web work. Okay, actually before I go and sort of start writing and showing you some examples, I just want to pause on this screen right here where I took notes for myself about what would be worth talking about from those web works. And so if you wanted to just sort of take a picture of this to know, kind of the more standard ones are problems 1 through 5, basically 8 through 13, and then there's these ones that have some tricks to them that I tried to write kind of briefly here. And then the trick for 14 is actually on your worksheet, so that's not really new. And then these two with stars I'm going to start out talking about. And then if we have more time at the end, I'll go ahead and talk about some of the later problems as well. It's just that nobody's really asked me about those yet, I think because you've not had a chance to get there yet. But I know that people have questions about problems 6 and 7. So problem 6 is going to be using that unit vector definition. I had written this. Let's just get rid of it. You don't need that saved anywhere. Okay, so problem 6 is that unit vector definition. I'm just going to steal the numbers from my web work right here real quick. So my point is P equal to 3, 2, and q equal to 15 comma 7. And I'm looking for a unit vector from P toward Q. And then a vector of length 39 in that direction. And while I was reading all that out loud, I wrote it right here just so that it would be saved somewhere. All right, so the first part, hopefully once you get to 6, is going to be kind of familiar, finding a vector from a point to another point. I don't know how to make that go away. So the vector PQ is going to be that vector that starts at Q, or sorry, starts at P and goes to Q. So I look at the difference from Q to P in the first component and the second component. So 15 minus 3 I got from that, and then 7 minus 2 I got from that. And so this is just going to give me 12, 5 is my vector from P to Q. And then I could go ahead and check what the length of PQ is. That's going to be the square root of 12 squared plus 5 squared. That's going to be, bringing this back on my worksheet, I learned that length is square root of all the components squared added together. And I wrote it with this double magnitude sign because I'm out of practice with how you all learn things. So we'll switch that back to the single bar. So that's square root of 144 plus 25, which is the square root of 169. And I'm not sure what that is. I'm just checking right now if it's a number. It is, it's 13. So that's the magnitude of the vector that points from P toward Q. And then since this vector has magnitude 13 from the worksheet, a unit vector has length 1. So I know that I don't have a unit vector right now. But if I divide a vector by its length, I'm going to have a unit vector. So going back to this problem right here, I'm going to say U is my unit vector. And if I start with PQ and I divide by the length of PQ, then I should have a unit vector. So PQ was 12, 5. The magnitude I found right here was 13. So my answer should be 12 over 13, 5 over 13. If you all are preferring the hat notation, that's going to look like this. I'll usually just do the angle brackets because they're a little bit easier for me, unless seeing the I's, J's, and K's helps to kind of combine terms. So then I could go ahead and go back to my web work and make sure that I did that right before I let you all go and use this approach for yourselves. 12, 13, 5, 13. And it worked. I haven't answered the second part though. Okay, so the second part is find a vector of length 39 pointing in the same direction. And so right here, you can multiply a unit vector by any number to obtain a vector in the same direction with a new magnitude. So what that means is my new, hold on, I'm going to write that this is a unit vector in direction PQ with length 1. And then some new vector V following that rule. If I just multiply by the magnitude I want, which I've already forgotten with all this talking, it's 39. So if I multiply by the length I want times a unit vector, I'm going to get a vector that has this length and points in the direction of this vector. And so that's going to be 39 times 12 over 13, 5 over 13. 39 over 13 is 3, so that's just going to be 12 times 3, 5 times 3. So that's 36, 15. And then we could go ahead and take the length of this vector. So if I do 36 squared, wow, my handwriting got really bad. If I do 36 squared plus 15 squared is going to be the formula for length, and I can't do that myself, so I'm going to go ahead and just bring this back real quick. 36 squared plus 15 squared, that's going to be 1521. Oh no, I wanted the square root symbol, that's fine. So square root of 1521 is 39, just like I wanted. So I'm going to go ahead and write that in my work here. That's square root 1521, which is 39. So V is a vector. Oh shoot, sorry, my screen turned off for some reason. V is a vector with length 39 in the same direction as U. And so my answer for the web work, what it actually asked me is right here. I just did this last part so you could kind of see that it does work. So that's how you do problem 6 if you were having trouble with it. And then problem 7, the geometry of it I don't think was holding anybody up. Kind of the equation of a sphere people seemed happy with. But what seemed to be tripping people up was that the form of this equation doesn't quite match the form of the equation on your worksheet. And so you need to complete the square so that that formula matches. And if it's been a while since you saw that, we're going to go ahead and go over it. Right now I'm just copying down that this equation is x squared plus y squared plus c squared minus 8x plus 10y equal to minus 5. I sure hope none of you have the same numbers as me in web work. So I've written down what we're given in web work. And what we want to have is x minus a squared plus y minus b squared plus c minus c squared is equal to r squared. And so we just somehow have to turn terms where the x squared is by itself to terms where it's kind of in this factored form. So I'm going to start trying to do that right here. And you all might have learned this a different way, so if you know a clever way to do it, go ahead and do that. I'm just going to do this the way that I learned in school, and your way might be different. But so I want this x squared to become something like x minus something squared. And if I start multiplying out x minus any kind of number squared, I know that I'm going to get x minus that number times x minus that number. I'm going to get like an x squared term, and then I'll get minus x times that number, minus x times that number, plus like that thing squared. And what's important is that my x squared already matches. So I don't have to worry about anything out in front of this x. It's just going to stay the way it is. And then if two of these numbers are going to come out of the squared, and I want them to simplify to minus 8x, I need this number to be half of what I already see in my equation. So if I do minus 4, then that squiggly line I drew is going to become 4 everywhere. Let me just do that. So x minus 4 squared is x minus 4 times x minus 4. I get x squared, oops, you always go in this order, minus 4x plus 16. Oh, I wrote it squared, plus 4 squared. Actually, to make that not confusing, I'm just going to write plus minus 4 times minus 4. And so this minus 4x would match that minus 8x. So we're good. But there's an extra plus 16 here that comes from those minus 4's multiplied together. And so this is covered inside my x minus 4 squared, but then there's also this extra plus 16. And so what I would have to do is just take away that extra afterwards. So if I did x minus 4 squared and got this extra 16, I can just right away take it away again. And so then I would be left with, that's just x squared minus 8x, which is exactly what I had up top. And then we just repeat it for the y. So y minus something squared is what I need to do. Since I have this minus 10y right here, let's see if I can do like a different color. There we go. Actually, I'm just going to erase those lines. I think they are too distracting. So I want to combine with this plus 10y. So that's going to have to be y minus 5, or y plus 5. So that would give us y squared plus 5y plus 5y plus 25. So that's y squared plus 10y, great. But then there's this extra 25 that we don't want, so we have to subtract that 25 again. And now in this case, what we would have is y squared plus 5y plus 5y plus 25 minus 25. Those last parts we don't want cancel out, and we just have the y squared plus 10y we were trying to match. So that part matches what we need. And then the z squared, there's no z term, so we don't have to do anything special there. So just z plus 0 squared is z squared. That part's already done. And what I'm going to do is I'm just going to replace in my equation what I found here with what it corresponds to here. And so now I have x minus 4 squared minus 16 plus y plus 5 squared minus 25 plus z squared is equal to minus 5. And then I want it to be in this form where all the squareds are on one side with the x, y, and z, and then with the radius just on the other side, the standalone numbers. So I'm going to go ahead and rearrange that. I've got x minus 4 squared plus y minus 5 squared, just because the form is to have that negative. Go ahead and put it in parentheses. Maybe it looks better. And then plus z minus 0 squared. And then I'm just going to add the 16 and 25 on the other side. That becomes minus 5 plus 25 plus 16. That's 36, which is 6 squared. So I've got x minus 4 squared plus y minus 5 squared plus z minus 0 squared is equal to 6 squared. So that maybe went a little bit slow, but at this point we have a sphere equation that matches the format we need to be able to read off the radius. So r is 6, and to be able to read off the coordinates of the center, a is 4, b is -5, and c is 0. So our center is going to be at 4, -5, 0. And if I go back to my web work, my radius was 6, and my center, I have to do like point notation for -5, 0. It asks you to write it as a point like that, where you just put commas between the numbers, but then it's good. So those are the two main problems that I've seen so far in class. So if you've gotten through like the first let me see the numbers again. Definitely the first 5, hopefully you've gotten through by now, and maybe 6 and 7 were kind of tripping you up because of just some challenges there, but hopefully if you needed help, this video did that. And then once you've gotten through those first 7, the 8 through 13 that come next should be pretty straightforward applying formulas. And so then I have time, I'm going to go ahead and talk through some more of the problems between 14 and 18 a little bit. Okay, so I brought back the web work of problem 14. And if you do run into problems on those ones that I'm saying are a bit more like applying a definition, definitely, ask me about it in class, ask your learning assistants about it, come to office hours. I'm happy to talk you through it. I just don't want to make this video exceptionally long to go over everything that might come up. I'd prefer that you just come talk to me so we can figure it out. So problem 14, I'm not going to work through a lot. I just want to kind of draw the picture for you so that you can maybe better visualize that note at the end about what we're doing. So right now my web work has that the point P is at 4, 0, 0, Q is at 0, 8, 0, and R is at 0, 0, 12. And then I've written that on my little notepad. And so just so you can actually, I don't have to draw this abstract. I can go ahead and draw it along the axes. It's a simple enough one. So here's my X, Y, and Z axes. So the point P is at 4, 0, 0. The point Q is at 0, 8, 0. And then the point R is at 0, 0, 12. So I just drew these going up by 12s. So that's P, Q, and R. And I'm interested in this kind of triangle between them that fills in that space. And then what I'm going to do is I'm going to think about two vectors from P to Q and P to R. So PQ is this vector right here, and it's going to be 0, -4, 8 minus 0. Sorry, my 8s are really bad. I always get questions about that. 8 minus 0, 0 minus 0. That's just -4, 8, 0. And then this vector right here is my PR. So I would find that by 0 minus 4, 0 minus 0, 12 minus 0. So that's just going to be -4, 0, 12. And the tricky part here is that the properties that you got in your worksheet talk about a parallelogram. So it talks about a parallelogram formed between V and U when they both sit at the origin, which they don't sit at the origin in this picture, but you can just imagine like shifting the origin over this direction so that it does sit at the origin, and nothing about what I've drawn would change, just that little coordinate system under it. So the parallelogram formed by PQ and PR would be this whole thing. And the web work asks you about this triangle, which is just half of it. So PQ cross PR is about the rectangle looking parallelogram. And we just divide by 2 to get the area of the triangle. And I'm going to call that the shaded region, and then I'm going to fill it in so that we have like a name to refer to that triangle by. Triangle PQR is that shaded region. So you would just go ahead and sort of that area is 1/2 times the magnitude of PQ cross QR. And then the other part of the problem, I think actually the first part, I may have talked about it out of order. Yeah, find a non-zero vector orthogonal to the plane through the points P, Q, and R. So the plane through the points P, Q, and R is this parallelogram I've drawn, basically. Plane actually goes on forever, so it would be something that has that angle and just cuts through this screen. And so the vector normal to it, orthogonal to it, is going to be like this. But from, you can see a drawing in the textbook, or just you can believe the sentence I wrote right here. The direction of the cross product is orthogonal to this plane or that parallelogram. So all you're going to do is you're going to compute your PQ cross QR, PQ cross PR, and then that direction matches the direction of the vector they're asking for. You can give just the cross product, or you can divide it by any number. It's fine. It doesn't ask for a unit vector, I don't think. So you can just leave it in whatever form you get it. Yep, just non-zero vector. So that's how you do that last problem. Really what I've said is the same thing as is written there, but I thought the picture might help it click a bit more. 15, I'm not going to like write or show anything for. Hopefully that description that you're just writing the vectors from the points like problem 1 and then doing the calculations like problems 3 through 5 will click. 16, let me see what I wrote on that first page. Yeah, I'm not going to write more here either. Just you solve for the angles the same as in problem 11 with the dot product definition in an algebra problem, basically. And then you just classify. I guess I could write for you all that acute is less than 90, obtuse is greater than 90. Is it that they just say right? Yeah, right angle. So if you didn't remember those, that's what those classifications mean. And then problem 17, I actually will kind of talk about a little bit more. I think I've got time. I'm just going to write down these numbers real quick. A is minus 105. B is minus 3, 5, minus 1. And P is K, K, K. How do I... Well, it's okay. I'll just move this there for now. Next time I'll figure out a way to show the web work and the screen better together, so I'm not always tapping back and forth. And we want to know when is AB perpendicular to AP. And we get to just solve for any number K that would go ahead and make that true. So whenever you see a problem asking you about perpendicular things, think dot product. So if the dot product is 0, the two things are perpendicular. You can think about that from the worksheet. You know that the dot product is the magnitude times the angle between them. And if they're perpendicular, the angle between them is 90. And cosine of 90 is 0. So two things that are perpendicular are going to have 0 dot product because the angle between them is 90 degrees. So then we can go ahead and construct AB and AP. Make an equation for the condition that they're perpendicular. And then solve for K. Those are going to be the 3 big steps. So for example, AB is going to be minus 3 minus 1, a bunch of components. So that's going to be minus 2, a bunch of components, for example. So be careful here. That same thing that's been tripping people up in the earlier problems. If you subtract a negative, it turns into addition. And then the AP might be a little bit intimidating, but you're going to do it exactly the same way. So it's going to be whatever the component of P is, which happens to be K, minus the component of A, which is minus 1. So in this case, it's going to be K plus 1, a bunch of stuff. I'm cutting out some details because I want you all to try this a little bit, and also we're running out of time for me to get to everything I wanted to talk about. So then the equation for them being perpendicular is that their dot product has to be 0. So my equation is 0 is equal to AB dot AP. But I have AB and AP right there, so I can go ahead and apply the dot product equation. There are 2 to choose from. There's one that depends on their lengths and their angle, and there's one that depends on their components. So if you look at what I have their components. So I'm going to want to use that component-wise multiplication one because it's what I have. I'm going to want minus 2 times k plus 1, etc. And then I would simplify that. And then in the end, I'm going to have an equation that has 0 on one side and a bunch of stuff that depends on k over here. And then I can just solve for k so that I get the 0 that I want. So hopefully that sketch of the approach helps you out. Next week during the problem solving session, you could go ahead and request that I go into this in more detail if you're still struggling with it. But this is kind of a fun problem. It goes a little bit backwards about using the dot product, I guess. So I think it'll be nice for you to explore with it a little. Next up is problem 18, which is this one with the components. It's the last problem of the homework, so if you get to this point, great. And all I really wanted to do here is sketch those component vectors. So I told you earlier that I hat is 1, 0, 0, j hat is 0, 1, 0, and k hat is 0, 0, 1. So in our coordinate system, I think I need to make this smaller. Okay. I hat is going to be this one out to 1. J hat is going to be this one, again out to 1. And k hat is going to be this one out to 1. And just what's important to know is that all of these are perpendicular to each other. They point in the directions of the coordinate axes, and coordinate axes are perpendicular to each other, and they have length 1. They're unit vectors. So when you're doing their cross products, you can kind of reason through using this idea. The direction of the cross product is orthogonal to the plane of the parallelogram formed between them, and the magnitude is the area of a parallelogram formed between them. So for example, if I was looking at I hat cross k hat, I could go ahead and think about, I've got my k hat right here and my I hat right there. So the parallelogram between them is this unit square. I didn't draw that very good. Maybe a bit more like that would preserve the angle of it. So each side is length 1, so the area is 1. So the magnitude of whatever I'm going to get is 1. Hold on, I got to pause this and get a charger. Okay. So the area between them is going to be 1. And then the thing that's going to be perpendicular to them is going to come out like this way. So that's perpendicular to the plane formed between those two vectors. And it happens to point in the exact same direction as j hat. So y-axis direction or same as j hat. So I hat cross k hat should have magnitude 1 and point in the direction of j hat. But that's just j hat, because j hat we already saw has magnitude 1. Actually, there's no point in me writing that separately. I'm just going to put it right there. So you can do this web work by using kind of reasoning like that. I'm told this comes really naturally to those of you who have had to mess with these in like physics classes before. But if you want to manually solve all the cross products, you're welcome to do that as well. The last thing I want to do, and I think I can do it in 7 minutes, is roll on back to the cross product problem, problem 13. So real quick, I'm going to copy down these numbers on my notepad, and then I will switch back to the screen where you can see what I'm doing. Okay, and what I want to do is just show the determinant form of the cross product real quick, if that's something you prefer to use. If you like to memorize the formula, that's okay too. I usually do this because then I don't have to memorize something, but everyone has their own preference. So here's my A, here's my B, and I'm trying to find A cross B. And so if you want to do the determinant approach, what you're going to do is make a 3 by 3 matrix where you put your I hat, j hat, k hat on top, the components that correspond to those for the first vector in the middle row, and the components that correspond for the second vector in the last row, like this. And then you're just going to compute the determinant the same way you might have learned in like a pre-calc kind of class, or linear algebra if you've taken it before. And if you've not taken it, I'll just show you the determinant. What you do is you go to the first entry, and you kind of block out everything that sits in a row or a column with that entry, and then you look at the numbers that are left over. You multiply along the main diagonal, and then you take away multiplying on the off diagonal, or the opposite diagonal. And then you repeat it for the middle component. So now I'm going to look at j hat. But the only tricky thing is that I actually subtract this part. I always go plus, minus, plus when I'm doing my determinants. So I subtract it, and then I block out everything that's aligned. And then I'm going to do multiplying the main diagonal. So I've got 1 times 1. And then I take away multiplying the opposite diagonal, so that's 1 times 5. And then I'm going to proceed with doing k hat next. So I add it, the only one I subtract is j hat, and then I ignore everything that lines up with k hat. And then I multiply, and then I subtract multiplying in the other direction. And so after I do that, I would just go ahead and simplify everything. So I've got 2 minus 7 I hat minus 1 minus 5 j hat plus 7 minus 10 k hat. So that's going to be minus 5 I hat. This gives me minus 4, and then the minus outside turns it into a plus 4 j hat. And then 7 minus 10 gives me minus 3 k hat. And I would write that in angle form like this, minus 5, 4, minus 3. And then I am always really bad at arithmetic, so I'll go ahead and check if that worked out right. Minus 5, 4, minus 3. And it did. It's correct. I haven't done the second one yet. If you prefer to use this formula, you can do that. I think I have time, so I could go ahead and do that now, but I don't remember this formula, so I'm going to go ahead and write it down. y1 z2 minus z1 y2, comma, z1 x2 minus x1 z2, comma, x1 y2 minus y1 x2. Okay. So I just crammed that formula right there. So I can also do that it would be y1 is 2, z2 is 1, z1 is 1. I'm underlining the one that it corresponds to each time in case that helps. And then y2 is 7. So x, y, z corresponds to the first, second, third components, and then 1, 2 corresponds to did it come from the first vector or the second vector. Then z1 is 1, x2 is 5, right there. X1 is 1, so minus 1 times that. Z2 is 7. Oops. X1 is 1. Y2 is 7. Y1 is 2. And x2 is 5, right there. So then we're going to get 2 minus 7, 5 minus 7. Oh, and something's already gone wrong, so I'll go ahead and figure out what I did wrong there in a second. And 7 minus 10. And then let's see what I did wrong here. I was supposed to be z1, which is 1. So I got that one. X2, which is 7. Oh, there we go. No, it was 5. I hate this formula. X2 was 5. X1 was 1. And Z2 was 1. That's where my mistake was. I did Y2 instead of Z2. So 5 minus 1 is actually what it should have been. And this is going to give me minus 5, 4, minus 3. So the formula gives you exactly the same answer as the determinant. Whichever one you're more comfortable with, you can use. If my attempting to use this one wasn't clear, this one I'm very uncomfortable with. I have a lot of trouble keeping all these numbers straight and remembering this formula to write it down. So this is the one that I usually do, and if I have to do one, I'll usually show it that way. But if you're happier with this version, just always pay attention and sort of in your own notes write it the way that you like it. And I think that's all I wanted to go over today. So I'm going to stop this recording and then get it uploaded.